Okay, Mina, you talked me into a short video on this exponential function business. So we're going to start with a little calculus, and the calculus will be to solve this equation where the left-hand side is a derivative. So the important thing, I guess, at first blush is the answer is a function. You want a function whose derivative is x squared. I look at these things kind of like a chain where up and down means take the derivative. So if you begin with 2x, you take the derivative, you get, if you begin with x squared, you take the derivative, you get 2x. Derivative of that is 2, derivative of that is 0, and then it's 0. This question is asking what's up here. What is here? And I think Asa got it right away in class. 2x, and then 2x plus any constant works. But there's kind of a mechanism for solving this. This mechanism was actually invented to solve this problem, this notation of derivative as change of y divided by change of x. And you treat these differentials as numbers. So dy is equal to x squared dx. And so now you can integrate both sides of this. And if you do, on the left-hand side, you get y. On the right-hand side, you get 1/3 x cubed plus a constant. And that is the answer to the question. 1/3 x cubed plus a constant. And it's a fact due to the fundamental theorem that any solution to this equation, this is called a differential equation because it has a derivative, any solution to a differential equation, to this differential equation, has this form. But any constant will make this true. So there's kind of a direct relationship. This is called the general solution. And general not in the sense of the military, but general in the sense that every solution has this form. Okay, so we did a couple of these. We talked about it a little bit. But the kind we're going to deal with, because of the fact that linear algebra will actually be the solution to this, we're going to look at ones where you have a y on both sides. It'll be something like this. Y prime equals, say, 3 times y. In words, this says if time is the x variable, so if y is a quantity given in terms of time, y of 1 means how much y you have at 1 year, y of 2, how much y you have at 2 years, and so on. And so if time is the x variable, then this says the rate of change, how fast y is changing, of whatever y is proportional to how much is there. And the proportionality depends on what you're talking about. So if you're looking about, if you're talking about frogs in the pond, then how fast the frog population increases depends on, at any given time, how many frogs are there. Now, of course, if you have too many frogs, they spoil the environment. So this is only under ideal conditions for producing y. if frogs get too populous, they will spoil their environment and it won't be healthy for them. And that might even mean this number becomes negative. But in general terms, if you have healthy populations that are changing, something like this is often true. It's definitely true now with the coronavirus. So let's see how to solve this equation. What is the solution to this equation? So we do a little math and see what it tells us. So dy dt, this time with the x variable as t, is 3y. So that says 1 over y is equal to dy is equal to 3 times dt. Then anti-differentiate, integrate both sides. Here we get the log of the absolute value of y. The absolute value sometimes is left off in calculus, but in applications, you don't want to leave it off. There are a lot of applications where absolute value is necessary here, or it gives you information you wouldn't have otherwise. The right-hand side, 3t plus c. Actually, each integral has a constant, but you can collect them together and just say anything like this. And solving this for y says the absolute value of y is equal to e, the base of the logarithm, raised to this power. And e raised to this entire quantity. It's not e to the 3t plus a constant. It's e to this entire power. And so the absolute value of y, doing a little arithmetic here, e to the 3t times e to the c. Like bases, you add the exponent. So y itself will be either equal to plus or minus e to the c times e to the 3t. And since c can be any constant and you're using plus and minus, traditionally you just replace it by a single letter. And usually it's a capital letter in this instance, A. So start here, the end is here. And this is called, again, the general solution. Not commander-in-chief kind of general, but it means that every solution to this has this form. And this is interesting because this is the so-called exponential growth form. What A is in this case, you can see pretty readily. If you substitute 0 for the variable t, this is A times e to the 0 power. So the population at time zero means when you start measuring or when your experiment begins. So that leading coefficient, the leading A term, is exactly the population where you began measuring. And this is, I would like you to know how to derive this, because it's important to know that every time rate of change is proportional to what's there, it results in exponential growth. And this is the exponential growth. And how fast it is exponentially depends on this constant. But if this constant is larger than 1, it grows very rapidly. Exponential growth is very rapid. All right. So this is the basic idea. So if we have something like y prime equals 32.2y, and you know that the population at time 0 is 14, then the solution to this is y equals the initial population, 14, times e to the 32.2 t. Even though you only start with 14 individuals, if the rate of change is this proportional, 32.2 times y. Growth is remarkably fast. This is hugely fast. Excuse me, I'll try to cut that out. No, I won't. I'll leave it in. Or, and these all work the same. Y prime equals 1/5 y. Let's say y of 0 is 102. Then the solution to this, y is equal to an exponential function times a constant. That constant is this constant, e to the 1/5 times t. Also, this is extraordinary growth, very fast, even though you have a 1/5 out in front. And all of these work the same. So for us, it's a good idea to remember how to get from here to here using this initial, this is called initial because it begins at 0, initial information. Now, a more sophisticated problem, and one that, or maybe before we do this, let's just say that we will generally use x's for our variables. So we'll have x is equal to, x prime is equal to 3x. And the variable involved will be time. T. So when I write this, inherent, there'll be a variable time. And this will say the rate of change of x, whatever x is proportional to x itself. So the solution to this, x is a function of t, will be some constant times e to the 3t. And if I tell you that the amount of x at time 0 is 42, then this is a specific, this is the general solution. The specific solution then is just 42, e to the 3t. So once you get the hang of it, this kind of equation gives this kind of solution. We're good to go. And we'll be dealing with equations where I'll use x's. We want to get a little more sophisticated here, though. So we're going to have a variable x, and x prime will depend on x itself. So maybe it'll be equal to 3x, but so x prime is proportional to x, but it's also proportional to y. So the rate of change, how fast x is changing, depends on how much x is there, but also how much y is there. So the rate of change of coronavirus depends on how much coronavirus is there. But it also depends on, say, the average distance individuals from the population stay from one another. There are other variables involved with how fast this is changing. And so this is a more general problem type. This is one that is more sophisticated than a simple one variable type. It's not all that sophisticated, but it's somewhat more sophisticated because here you have two variables and they interact with each other in a complicated way. The same thing happens with drugs that you might be taking for various illnesses. There are interaction together. How one changes you depends on the two that you have, and the rate of change of how the other one does depends on this type of interaction. So, this series of differential equations is frequent in medical science also. So this is the system that we're going to have, and we'll write this system as a matrix. So x prime y prime will be equal to the matrix 3 minus 1, 1, 1. times xy. So this is how we'll write it. Or xy, the quantity prime, is equal to this matrix 3 minus 1, 1, 1 times xy. Now, I didn't make this up to have specific eigenvalues and eigenvectors. I probably should have. So the next part is kind of pretend. If this matrix wasn't what it is, but was rather a diagonal matrix, 2, 0, 0, 3, then we could already solve this problem. This would be easy to solve. Because multiplying back through would tell you that x prime, y prime is equal to x, 2x, 3y. So this breaks up into two equations and two unknowns that we can solve. The first equation is x prime equals 2x. The second equation is y prime equals 3y. This one, x is a function of t, is some constant times e to the 2t. And this one is y is equal to another constant, so maybe I'll call them y1 and y2, e to the 3t. This is the solution. If we knew what the initial populations of x and y were, then we'd know a1 and a2. We would have the exact solution. The solution here, let's suppose that a1 is 1 and a2 is 2. Then the exact solution tells you that x would be equal to e to the 2t, and y would be equal to 2 e to the 3t. This is the solution to that system of equations. And what's it good for? This is good for prediction. If t is 0, you get the initial populations 1, 2. If t is 1, that happens in the future. If t is 1, that tells you that the population of x would be e squared, a little bit less than 9. And y would be 2e to the 5th. E to the 5th is about 250, so this would be a 500. So even though they start out at 1, 2, after t is 1, there's a huge discrepancy between these populations. And you can predict it from knowing how these two interacted and knowing what their initial populations were. So these predictions that we're doing on the spread of coronavirus are similar to this. They're more sophisticated, they have many more variables, but they are similar to this. And these predictions are based on what we know and what we're finding out about the rates of change of people who wear masks, people who don't wear masks, how fast the virus infects people, and so on. And both the death rate, which is the derivative, and the rate of infection, which is the rate of coronavirus present in the human population, those two rates depend on the variables involved that we're talking about. So we're doing a less sophisticated example of what's going on in our lives right now, but it is at the heart of how humans understand these things scientifically, mathematically. In any case, Mina, this is the best I can do. But I will see you on Monday. We'll talk a little bit more about this, talk a little bit about the exam. I've got a few cookies to make. See you soon.